Welcome students, welcome to steam turbine class. In the previous lectures we have already learned about the impulse turbine and the reaction turbine and the enthalpy drops and this kind of things. So let's talk about the losses in steam turbine. So there are certain losses taking place during the expansion of steam within a turbine. So these can be divided broadly into two groups. The first one, this one, is the internal losses and which are connected with the flow of steam, and second one is the external losses. Okay, so external losses may also then further we can divide into certain groups. So first one is the losses in regulating valve. As the steam before entering the turbine passes through the main valve and the regulating valves, the flow through this being accompanied by the pressure losses, the steam gets throttled adiabatically with constant enthalpy. However, the enthalpy drop in the turbine decreases, yielding less specific output. Thus, some adiabatic energy of the steam is lost due to the irreversible process of throttling. So, this pressure drop varies from 3 to 5% of the inlet steam pressure. Okay. So the second one is the nozzle friction loss. The friction losses in the nozzle were already mentioned earlier. Okay, so the effect of friction that can be taken care by the nozzle efficiency. The losses due to the growth of boundary layer and the formation of eddies in the wake, apart from the frictional resistance of walls, which varies with the height of and the length of the passage. The losses are higher in a turbulent boundary layer than in a laminar one. Okay, in the reaction turbine, where the pressure or enthalpy drop per stages is less due to the lower velocity, the laminar conditions persist over a greater length of passage. So the friction losses is less than the impulse stage. However, due to the large number of stages, the total surface area exposed to flow is more, which increases the friction losses. Thus, the nozzle losses depends on its size, the surface roughness, its length, the roundness of entrance, the divergence angle, the space between the nozzle, moisture and trailing edges. Okay. Now the blade friction losses. Okay. So losses in moving blade are caused by the various factors. We can list. We can again divide the blade friction losses. These are impingement losses. The steam issuing out from the nozzle meets the leading edges of the blades, and the energy may be lost if the entry is not smooth enough and eddies are formed. Okay, second one is friction losses. The steam encounters these losses in the blade passages, which depends on the roughness of the blade surface. Third one is the turning losses. These occurs as the steam turns in blade passages. Fourth one is the wake losses. This occurs at the blade exit depending on its shape, tip and thickness. So the moving blade losses are taken care by the blade friction coefficient, that is VR2 by VR1, this ratio representing the reduction of relative velocity of stream from VR1 to VR2 due to the friction. So in external losses, the fourth one is the disc friction losses. Disc friction losses. So when the turbine disc rotates in a viscous stream, there is a surface friction loss due to the relative motion between the disc and the stream particles. Due to the centrifugal force, the stream thrown radially outward. The moving disc surface exert a drag on the steam, sets it on motion from the root to tip, okay, and and produces a definite circulation. Some part of the kinetic energy of steam is lost due to this friction, okay. Now then, the partial admission loss, an impulse stage operating with partial admission or an early stage in such a turbine with nozzle provided only over a part of the blade periphery, which have the blades idle during the part of revolution. Some portion of the kinetic energy of the incoming steam is spent in clearing away the steam existing within the blade passage, and this called scavenging losses, which together with the friction losses and often referred to as the windage losses, in which some kinetic energy is imparted to the fluid at the expense of the kinetic energy of the blades. Since the reaction turbines are designed for full peripheral admission, the windage losses as well as the disk friction losses can be neglected. Okay. So then, the partial admission losses. Now the residual velocity losses. The steam leaving at last stage of turbine has a certain velocity which represent an amount of kinetic energy that cannot be imparted to the turbine shaft, and this thus wasted. Okay. Now then the carryover losses. Some energy loss takes place as the steam flows from one stage to the next. The kinetic energy leaving one stage and available to the next stage, it can be already written as, one second, it can be written as, I am obtaining here, that is N efficiency CO suffix CO into V square by 2. Okay, so this is the kinetic energy, where NCO is the carryover efficiency. In addition, there are some losses of energy due to the wetness of steam, where the water particles are dragged along with steam at the expense of some kinetic energy of steam. If the quality of steam is less than the 0.88, the erosion and also corrosion can takes place. Since the velocity of steam leaving the last stage of turbine is quite large, that means 100 to 120 meter per second, there will be energy losses due to the friction in the exhaust hood of the turbine. The exhaust hoods to the condenser gradually increases the area like a diffuser, and thus there is further decrease in velocity of steam and an increase in pressure as steam enters the condenser. Such hoods allow the turbine to operate between the slightly lower pressure than the required by the condenser, depending on the temperature and flow of the cooling water and the extraction from itself, thus the increasing the turbine work. Okay. Now the other external friction losses. Okay, there are some other energy losses in the bearings and governing mechanism which can be reduced by improving the lubrication system, and some energy is consumed by oil pumps. Since the turbines are adequately installed, the surface heat loss by radiation and convection is small. The modern large electric generators are hydrogen cooled and well designed and very efficient, where the energy losses are within 2 to 3%. Okay. Now the last one is the gland leakage losses. Now the last one is the gland leakage losses. The leakage of steam occurs between the stages and also the shaft and inlet and exit ends of the casing. The diaphragm leakage takes place in both impulse and reaction stages through the radial clearance between the stationary nozzle diaphragm and the shaft or drum. The tip leakage occurs in the reaction stages through the clearance between the outer periphery of the moving blades and the casing between because of the pressure difference existing across the blades. Okay, so the shaft leakage occurs through the radial clearance between the shaft and the casing at both height and low pressure ends of turbines. At high pressure end, the steam leaks out to the to the atmosphere, while at the low pressure end, the pressure being less than the atmospheric, and air leaks into the shell. Since the leak steam does not work on the blades, it represents energy loss. Both the diaphragm and tip leakage can be minimized by reducing the radial clearance, but it must avoid the rubbing or metal to metal contact. The clearance may be as low as 0.5 millimeter. However, the proper balancing of the rotor, both static and dynamic, is must to be avoided by such rubbing. Okay, it is necessary to use shields or packing to further reduce the leakage flow. These shields may be labyrinths, carbon rings, the water or steam seal, or gland leak off. To prevent the shaft leakage, the labyrinth may be used with carbon rings and gland leak off. The labyrinth seals consist of various thin strips fixed with casing with maintain the small possible clearance with the shaft as shown in this figure. Okay, these are the blades. Okay, and this is the labyrinth seal as shown, as you can see. And so, and this is the delta, this small amount of leakage is occurs in this case. Okay, the small constructions may make the steam throttle to low pressure many times till only a very little quantity leaks out. Okay, as shown in this figure. So the carbon ring shields, which consist of a ring of carbon divided into segments, have rings fit snugly to the shaft by spring so as to prevent the leakage, and may used along with labyrinth glands in series in large turbines. Okay, so these are the losses of turbines. Now we are going to learn about the reheat factor and conditions line. Now let's talk about the reheat factor and the condition line. So as shown in this figure, this one, the typical stage efficiency of simple impulse, kurtis and the reaction stages, and which demonstrate the variations of the blade efficiency versus the velocity ratio graph. Okay, as discussed in previous lectures, that there are various losses in the stages, and the portion of available energy is not converted to the work, and the remaining fluid is termed as the reheat. A single stage expansion with reheat is shown in this figure, in this one. The single stage expansion with reheat is shown here. So now we can write the isentropic enthalpy drop. The isentropic enthalpy drop, that is delta H suffix S, is nothing but H1 minus H2S. This is the isentropic enthalpy drop. One second. This is the isentropic enthalpy drop, and the actual enthalpy drop we can write delta H is equals to H1 minus H2. This one is the actual enthalpy drop. Actual. Okay. So the reheat enthalpy drop we can write reheat enthalpy drop, that is nothing but H2 minus H2S. Okay, H2 minus H2S. This is the reheat enthalpy drop. So as shown in this figure, shows the expansion in a 4-stage turbine taking into account the effects of reheat. The following conclusion, we can say that the reheat takes place with the increase in entropy. The reheat in a given stage is available to the work in the succeeding stage, except the last stage where the reheat is a loss. Okay, the constant pressure line uh, diverge from one to another, thereby increasing the enthalpy drop for the same pressure drop. Because of the number 2 and number 3 conclusion, the sum of available energies, that is isentropic enthalpy drop for each stage, is greater than the available energy, that is isentropic enthalpy drop for whole turbine. And the last one is the condition representing the actual expansion in the turbine is approximately the locus of point including the actual conditions of the steam at the exit of each stages. The effect of item 4 is expressed assuming the equal available energy per steam, per stage. So by the term called the reheat factor, the total isentropic enthalpy drop we can write as the total isentropic enthalpy drop, that is H total, is equals to nothing but H1 minus H6S is the isentropic total isentropic enthalpy drop. Okay, and it is divided equally into 4 parts in the 4 stages. In the Mollier diagram, from which the interstage pressure, that is P1, P2, P3 are noted, the P0 and P4 being the boiler and condenser pressure. This one is P0 and P4 respectively, boiler and condenser pressures. So the isentropic enthalpy drop, that is H1 minus H2S in the first stage, is multiplied by the stage efficiency to obtain the actual enthalpy drop, that is H1 minus H2, which is cut off from 1 on the isobar at P1 in the Mollier diagram. P1 in the Mollier diagram. Okay, so and from 2 the vertical line is drawn which cuts the isobar at P2 at same state, that is 3S. The isentropic enthalpy drop, that is H2 minus H3S, is noted, and the actual drop, that is H2 minus H3, is estimated by the multiplying it with stage enthalpy. In the same way, the enthalpy drop, that is H3 minus H4S and H4 minus H5S, are obtained from the Mollier diagram. And the state, that is 5, which is fixed. Okay, the state 2, 3, 4 and 5 recorded the actual conditions of steam exit from each stage, and the locus through this state is called the conditions line. The locus through these states is called again the condition line. So so the reheat factor is defined as you can see that is RF is the reheat factor equals to H1 minus H2S plus H2 minus H3S plus H3 minus H4S plus H4 minus H5S by H1 minus H6S, the total enthalpy, isentropic enthalpy drop. Okay, so these are the enthalpy drop. The H1 minus H2S is the first stage isentropic enthalpy drop, plus H2 minus H3S is the second stage isentropic enthalpy drop. Similarly, H3 minus H4S is the third stage enthalpy drop, isentropic enthalpy drop. Then H4 minus H5S is the fourth stage enthalpy drop. And the stage enthalpy, the stage efficiency can be written as, that is, eta stage is equals to, this is the actual enthalpy drop H1 minus H2 by the stage enthalpy drop, by the isentropic enthalpy drop. H1 minus H2 is the actual enthalpy drop, and H1 minus H2S is the isentropic enthalpy drop. Similarly, that will be equals to the second stage actual enthalpy drop H2 minus H3 by the second stage isentropic enthalpy drop H2 minus H3S. Similarly, for the third stage, the actual enthalpy drop is H3 minus H4 by the isentropic enthalpy drop, that is H3 minus H4S. And for the case of fourth stage, the actual enthalpy drop is H4 minus H5 by the isentropic enthalpy drop, that is H4 minus H5S. So from this expression, we can just substitute the isentropic enthalpy drops in this reheat factor. So we can write the reheat factor, this reheat factor is equals to H1 minus H2 by the stage efficiency is plus the H2 minus H3 by the stage efficiency plus H3 minus H4, the actual enthalpy drop by the stage efficiency, plus for the fourth case, the actual enthalpy drop for fourth stage by the stage efficiency, divided by the total isentropic enthalpy drop. So by simplifying this equation, by simplifying this above equation, we get reheat factor that is equals to 1 by the stage efficiency into H1 minus H5 by H1 minus H6S. So this H1 minus H5 by H1 minus H6S is the internal efficiency. So the reheat factor becomes the internal efficiency by the stage efficiency. So we can write, that is, internal efficiency is equals to reheat factor into the stage efficiency. And since the reheat factor is lies between 1.04 to 1.08, okay, so therefore we can say that due to the divergence of the constant pressure lines, the reheat factor is greater than the unity, and it lies between this. So also we can say that, so the internal efficiency is must be greater than the stage efficiency. Okay, thank you. So in this lecture we have learned about the different turbine losses and the reheat factor and the conditions line, and in the next lecture we will learn about the design of multi-stage turbine and the control of steam turbine. Okay, thank you.